Chapter 6, Bending, Part C, Derivation of Shear and Moment from Loading. Just consider we have a cantilever beam handling a distributed load of W, and we just want to observe the effect of internal loading on this cubic element. So if we just take this cube out of this structure and observe the forces, we can observe that if at the left we do have a shearing, a vertical force, and as if you travel by length of delta x to the right, the shear increases and reach to v plus delta v, and at the top the effect of distributed load. So summation of forces in y direction goes zero, gives us the forces at the right should be cancelled out by the distributed load and the shear at the left. So v minus wx times delta x minus v plus delta v goes zero, gives us delta v is equal to a negative wx dx. Dividing both sides by delta x and let delta x goes to zero in a limit condition, and that gives us a dv over dx is equal to a negative wx. And what that says, dv over dx is equal to a negative wx is just says a slope of shear diagram is a intensity of distributed load at the top, and just this negative sign is just the direction of the distributed load. If distributed load is downward, that's a negative. If it's upward, that's a positive. In other words, if we just take the dx to the other side, to the second part, and just integrate both sides. So integration of dv integrate is equal to integration of wx dx. Integration of deviation is the function itself, so that's shear is equal to integration of wx dx. And that says change in shear v is equal to area under loading curve. That's the that's another uh, explain of the same formula. But we just rearranged it and explain it in the other way. Mhm. That was the relation between load and shear. Now let's see what is the relation between shear and moment. If we apply if we add the two moment, one m and the other is m plus delta m due to travel to the left hand side. And if we just develop the summation of moment, and we just consider the counterclockwise as a positive moment about any arbitrary point, for example, O here. Summation of moment about O goes zero, and that gives us m plus delta m, which is a counterclockwise positive, plus the effect of distributed load, a half of a half of delta x, wx delta x, minus a v, which is the counterclockwise, and that's a minus m, which is another uh, clockwise, which is a negative. And delta m, if you simplify the equation, gives you v times delta x minus half of wx delta x squared. Again, if we rewrite the equation and dividing both sides by delta x, it yields dm. If you just ignore the uh, second delta x squared, due to delta x itself is a small amount. It's if it's you squared a very small amount, it's almost negligible. So in that terms, we just ignore that term. Dm over dx is equal to v, and that says a slope of moment diagram is a shear uh, value. Mhm. And if you just put it in a integration format, it just says m change in moment is equal to the area under shear diagram. let's put it in an example to grasp the meaning of what the gist of the formula a in a practice. So if we just have a two simple support beam and a concentrated load applied at somewhere a little bit after the center from the left side. So it's 6 meters, the other is 4 meters. If it was five, it was at the center. Before solving it, let's solve the problem in a parametric way to see how what's happened to the supports. So just consider uh, we have support A, we have support B, and we have a length of A from support A, and we have a length of B from the other side. So in that terms, if the load was at the center and my hand is holding it's opposing the applied force of P, each of my hands handle an equal force of P over 2. But if you just move the force a little bit to the other end, which is B, support B should handle a little more weight than 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 my left hand. So that's the concept. So let's say how the uh, forces distributed among the supports. So one can say Ra is P times B over L, the other half. So let's put it this way. Ra just goes by the length of the other side, and at the same time Rb it just goes by P times A over L. Mhm. If you want to put that in our problem, it just simply says Ra, just assume these are R and B. Ra is P, which is 4K, length is 10, length of the other side is B is 4, and Rb is equal to a P uh, A over L, and A is, this is B, this is A is 6, and L is 10. So Ra is 4 times 4 is 16 times 10, 1.6 kilonewton. And if this is 1.6, Ra should be 2.4 because the summation of them should goes by 4 kilonewton. And if you do the mass, it just gives you 24 kilonewton. And if you don't want to go this way, and that's the easier approach, just do like a normal condition, summation of moment about any support, and it just goes by zero, uh, and it just says a force of -4 times the length of 6 meters should be cancelled out by RB times 10, which is the total length. And it just gives you RB equal to 10.4. And as soon as you have the one of them, you can, by just going by summation of forces in y direction, should go 0, or should RA plus RB should equal to 4, then it just gives you RA, which is the same numeric value we got earlier. Mhm. And then if you want to draw the shear and moment diagram, let's make it a bit cleaner and just go by shear. So at the very beginning of shear, it just comes up by the amount of RA. So that's 1.6, and this is 2.4. And it just moves to the right all the way because there is no nothing from A to C to the to the location of load. There is no nothing, no force to affect my shearing diagram. So it just comes by a straight line. And all of a sudden at C there is a 4K downward step. So it just takes us to a negative 2.4. So that's a 1.6 minus 4. a step down, and if you just move from the force to the end, there is no other forces, so it just comes all the way to the right, and all of a sudden there is a support which takes us 2.4 up. So again, it was 2.4, it is a 4 minus 4. This is positive 1.6, it's a negative 2.4, and this is a positive 2.4. That's how easy you can draw the shear diagram just by following the forces and observing the external or other external forces on the beam. So let's see what's happened in moment. Mhm. Do you remember we told the area under? Okay, let's first of all, uh, is there any? We don't have any moment at these supports because it's not fixed. It's one of them is a ball and the other is a pin, so they are not in like a fixed support, so there is no moment. We have moment only at fixed support, like a cantilever beam. So we just simply know it should be zero at the beginning, it should be zero at the end. And if you remember, we talk about the area under shear, is the change of moment. So if you want to draw the moment diagram, it just goes by a positive area under here, and that's a 6 times 1.6. That's a 1.6 times 6 meters, and that's a 9.6. And then all of a sudden a negative area of should takes us back to 0. And if you want to verify that, you can just multiply 2.4 by 4. And if you do that, it just gives you again 9.6, which is the amount of or the height of this graph. And it's again the area under shear. The area under shear is the numeric value for moment. Mhm. We'll discuss, we'll practice more example in next videos. Thank you.